You are sitting somewhere quiet right now, perhaps in a room you know well, or a place you've been 100 times before. The world around you feels steady, solid. The walls stay where they are. The floor beneath you doesn't shift. And time, well, time just moves forward, doesn't it? Second after second, minute after minute, at a pace that feels constant, universal, the same for you as it is for everyone else on Earth. This is how we experience reality. Space seems like a fixed stage where everything happens. Time flows like a river, carrying us all downstream together at the same speed. When you check your watch and see that 10 minutes have passed, you assume those same 10 minutes have passed for everyone, everywhere. It's such a basic assumption that we rarely even think about it. It's just how the world works. Close your eyes for a moment and feel time passing. There's something almost tangible about it, isn't there? You can sense it moving, pulling you forward from one moment to the next. You remember what happened 5 seconds ago. You anticipate what might happen 5 seconds from now. And in between, there's this present moment, this now, that feels absolutely real and immediate. We build our entire lives around this feeling. We make appointments, trusting that everyone will experience the same flow of time between now and then. We celebrate birthdays, marking the passage of years that we assume have passed the same for everyone. We look at photographs from the past and think of those moments as finished, gone, while the present is happening and the future hasn't occurred yet. This is such a deeply ingrained part of how we think that questioning it feels almost absurd. Of course, time is the same for everyone. Of course, space is fixed. Of course, reality is objective, the same regardless of who's observing it. But what if none of that is actually true? What if time doesn't flow the same way for everyone? What if the space around you isn't really fixed at all? What if both space and time are part of something deeper, something woven together in ways we can't directly see or feel, something that bends and stretches and changes depending on how you're moving through it? What if the steady, reliable world you experience is just a narrow slice of something far stranger? More than a century ago, a young physicist working in a patent office in Switzerland had an idea that would completely transform our understanding of reality. His name was Albert Einstein, and the idea he introduced wasn't just a small correction to existing physics. It was a complete reimagining of the fabric of existence itself. He called it spacetime. At first, the concept sounds simple enough. Space and time aren't separate things. They're connected, woven together into a single structure that everything in the universe moves through. But as you dig deeper into what this actually means, the implications become stranger and stranger. Time can pass at different rates depending on how fast you're moving. Space can curve and bend around massive objects. Two people moving differently through the universe can experience reality in fundamentally different ways, and both of them would be right. Even today, more than 100 years after Einstein first proposed these ideas, we're still grappling with what they really mean. We can use his equations to make incredibly precise predictions. We've tested his theories thousands of times and found them correct again and again. But understanding the mathematics isn't quite the same as understanding what it all means for the nature of reality itself. This is a journey into one of the most profound ideas in all of science. We're going to start with the familiar, with the world as we normally experience it, and then slowly, gently, we're going to pull back the curtain and look at what's really happening beneath the surface. We're going to explore how time can slow down, how space can curve, how reality itself can be different depending on your perspective. And if you find yourself getting lost along the way, that's okay. These ideas are genuinely strange. They contradict our everyday intuition. But that strangeness isn't a flaw. It's a window into something deeper about the universe we inhabit. The journey ahead will take us from the familiar to the extraordinary, from the simple to the profound. We'll move slowly, taking time to let each idea settle before moving to the next. We'll use analogies and thought experiments, concrete examples and philosophical reflections, and throughout, we'll maintain a sense of wonder at how strange and beautiful the universe truly is. Before we go further, if you're enjoying this exploration, consider liking this video or subscribing to the channel. It helps us continue creating content like this, and it lets us know you'd like to see more deep dives into the mysteries of space and science. Now, let's begin where Einstein himself began, with the world as we think we know it. When the old certainties cracked, for thousands of years, humans looked up at the sky and tried to make sense of what they saw. The sun rose and set. The moon changed its shape. The stars wheeled overhead in patterns that repeated with the seasons. And through all of that, certain things seemed absolutely certain. Space was space. It was the emptiness between things, the stage on which everything played out. You could measure it, map it, move through it. If you walked a mile, that mile was the same whether you walked it quickly or slowly, whether you walked it on Earth or on the moon. Distance was distance, fixed and absolute. Imagine ancient astronomers carefully tracking the movements of planets across the night sky. They were mapping space, creating models of how celestial objects moved through the fixed arena of the heavens. Some thought Earth was at the center, with everything revolving around it. Others, like Copernicus, realized the sun was at the center of our local system. But all of them assumed that space itself was unchanging, a cosmic grid that existed independently of what moved through it. Time was time. It flowed forward at a constant rate, the same for everyone, everywhere. A second on Earth was the same as a second on Mars, was the same as a second in the farthest reaches of the galaxy. When something happened, it happened at a specific moment, and everyone in the universe would agree on when that moment was, even if it took light years for them to find out about it. This assumption went so deep that people barely noticed they were making it. Time was like an invisible river, carrying everything forward at the same steady pace. You could measure it with clocks, mark it with calendars, but you couldn't change it or affect it. It simply was, flowing independently of everything else. This way of thinking about the universe was formalized by Isaac Newton in the 1600s. Newton's laws of motion and gravity could predict the movements of planets with astonishing accuracy. His framework assumed that space was like an invisible, unchanging grid stretched across the entire universe, and time was like a universal clock that ticked at the same rate for everyone. Newton himself described this beautifully in his Principia Mathematica. He wrote of absolute space, which, in its own nature, without regard to anything external, remains always similar and immovable, and absolute time, which flows equably without regard to anything external. This was a powerful vision. Space and time were the eternal stage on which the drama of the universe played out. They were not affected by that drama. They simply provided the framework within which everything else happened. For more than 200 years, this picture of reality worked beautifully. It explained why apples fell from trees, why the moon orbited Earth, why the planets moved in their precise paths across the sky. It allowed scientists to calculate the positions of celestial objects years in advance, with incredible precision. Astronomers could predict when eclipses would occur, when comets would return, when planets would align. Engineers could use Newton's laws to build machines, calculate trajectories, design structures. The physics worked, and it worked magnificently. But there were hints, even in Newton's time, that something wasn't quite right. Newton himself was troubled by one aspect of his theory of gravity. According to his equations, gravity acted instantaneously across any distance. If the sun suddenly disappeared, Earth would immediately feel the loss of gravitational pull and fly off into space. But how could this be? How could something here instantly affect something billions of miles away? What carried that influence across the void? Newton admitted he didn't know. He famously wrote that he would not feign hypotheses about the mechanism of gravity. It simply was. The mathematics worked, and that was enough for practical purposes. But the philosophical problem remained. Action at a distance, instantaneous influence across empty space, seemed deeply mysterious. Another problem emerged in the 1800s when scientists began studying light and electromagnetic waves. The work of Michael Faraday and James Clerk Maxwell revealed that light was an electromagnetic wave, an oscillation of electric and magnetic fields traveling through space. But according to their understanding, waves needed something to travel through. Sound waves travel through air. Water waves travel through water. So what did light waves travel through as they crossed the empty vacuum of space? Scientists proposed that space must be filled with an invisible substance they called the luminiferous ether, or just ether for short. This ether, they imagined, permeated all of space, filling the void between stars and planets. Light waves, they thought, rippled through this ether the same way sound waves ripple through air. And if the ether existed, then you should be able to measure Earth's motion through it. As Earth moved through the ether, there should be a kind of cosmic wind, detectable by very precise experiments. Light traveling in the direction of Earth's motion through the ether should move faster, while light traveling against Earth's motion should move slower. In 1887, two scientists named Albert Michelson and Edward Morley conducted one of the most important failed experiments in the history of physics. They built an incredibly sensitive device called an interferometer to measure Earth's motion through the ether. The device split a beam of light, sent the two halves in perpendicular directions, bounced them off mirrors, and brought them back together. If Earth was moving through the ether, one beam should take slightly longer than the other, and this would create a detectable interference pattern. They expected to find that light traveled at different speeds, depending on which direction it was going, faster or slower depending on whether it was moving with or against the ether wind. But they found nothing. No matter which direction they measured, no matter what time of day, no matter what time of year, light always traveled at exactly the same speed. This was deeply puzzling. It suggested that either the ether didn't exist, or something very strange was happening to space and time that made the ether wind undetectable. Scientists tried various explanations. Maybe the ether was dragged along with Earth, creating a bubble of stationary ether around the planet. Maybe the measuring instruments contracted as they moved through the ether, shrinking in just the right way to cancel out the expected effects. One physicist, Hendrik Lorentz, developed mathematical equations describing how objects would need to contract and how time would need to slow down to explain the null result. But these were seen as mathematical tricks, not descriptions of real physical effects. The real answer turned out to be far more radical than any of these proposals, and it required completely rethinking what space and time actually are. The stage was set for a revolution. The old certainties were beginning to crack. The ether couldn't be found. Light behaved in strange ways. And a young patent clerk in Switzerland was about to change everything. The patent clerk's revolution. Albert Einstein was 26 years old when he published the paper that would change everything. The year was 1905, and Einstein was working at the Swiss Patent Office in Bern, evaluating patent applications during the day and thinking about physics in his spare time. He wasn't working at a major university. He didn't have access to expensive laboratory equipment. He had no research grants, no team of assistants, no prestigious position. What he had was a deep curiosity about the fundamental nature of reality and a willingness to question assumptions that everyone else took for granted. Einstein's path to this moment had been unconventional. He had struggled in school, not because he wasn't brilliant, but because he chafed at authority and rote memorization. He had trouble finding academic positions after graduation. The patent office job was steady work that paid the bills, but it wasn't what he had imagined for himself. Yet in some ways, the patent office was the perfect place for Einstein. The work was interesting enough to engage his mind, but not so demanding that it consumed all his mental energy. He had time to think, and think he did, deeply and persistently about the fundamental questions of physics. Einstein had been thinking about light for years. One of his earliest thought experiments, which he conceived as a teenager, was simple but profound. What would it be like to ride alongside a beam of light, traveling at the speed of light yourself? According to Newton's physics, if you were moving at the same speed as a light wave, the light would appear to stand still relative to you, frozen in place like a snapshot. You could, in principle, examine this frozen electromagnetic wave, see its peaks and troughs suspended in space. But the equations of electromagnetism, developed by James Clerk Maxwell, suggested that light couldn't stand still. A stationary electromagnetic wave didn't make sense mathematically. It would violate the fundamental equations that describe how electricity and magnetism work. Maxwell's equations had no solution for a static light wave. This contradiction bothered Einstein deeply. And as he thought about it more, he began to realize that the problem ran deeper than just light. It had to do with the very nature of motion, space, and time. Think about what it means for something to be moving. In Newton's physics, motion is always relative. You're only moving relative to something else. If you're sitting in a train moving at a steady speed, and the curtains are drawn, you can't tell if you're moving or not. There's no experiment you can do inside the train that will tell you your absolute velocity through space. This is called the principle of relativity, and it dates back to Galileo. The laws of physics are the same in all reference frames, moving at constant velocity. There's no privileged state of rest, no absolute motion. But here's where it gets interesting. If the principle of relativity is true, then the speed of light should be the same in all reference frames. It shouldn't matter if you're moving toward a light source or away from it. You should always measure light traveling at the same speed. But that seems impossible. If light is moving at a certain speed and you're moving in the same direction, shouldn't you measure it going slower relative to you? Einstein made a bold decision. Instead of trying to explain away the strange results of the Michelson-Morley experiment, instead of inventing complicated mechanisms to preserve the old way of thinking, he took the results seriously. He accepted that light truly does travel at the same speed for everyone, no matter how they're moving. This wasn't just accepting an experimental result. It was elevating it to a principle, a fundamental law of nature. The speed of light is constant, the same for all observers, regardless of their motion. And then he worked out what that simple fact implies about the universe. The conclusion was startling. If the speed of light is the same for everyone, regardless of their motion, then space and time cannot be absolute and universal. They have to be flexible. They have to change, to adjust, to be different for different observers, all in precisely the right way to ensure that everyone measures the same speed of light. Think about what this means. Imagine you're on a train platform and a train passes by at high speed. Someone on the train shines a flashlight in the direction the train is moving. You measure the speed of that light. The person on the train measures the speed of that light. According to common sense, you should measure different speeds. The light should be moving faster relative to you than it is relative to the person on the train. But according to Einstein, you both measure exactly the same speed. The only way this can work is if your measurements of distance and time are different from the train passengers' measurements. Space and time themselves must be flexible, must change depending on motion, in just the right way to keep the speed of light constant. This was the core insight of what we now call special relativity, and it led to a completely new way of understanding reality. Einstein published his paper on special relativity in 1905. It was titled On the Electrodynamics of Moving Bodies, and it was remarkably simple and elegant. No complex mathematics, no lengthy derivations, just clear reasoning from basic principles. The paper began with the two postulates we've discussed: the principle of relativity and the constancy of the speed of light. And from these two simple assumptions, Einstein derived everything else: time dilation, length contraction, the relativity of simultaneity, the equivalence of mass and energy. All of it followed logically from those two principles. It was a masterpiece of theoretical physics, and it changed our understanding of the universe forever. The fabric that connects everything. Here's where we need to slow down and really think about what Einstein discovered. Because the idea of space-time, the central concept that emerged from his work, is both beautifully simple and deeply strange. Let's start with how we normally think about moving through the world. Imagine you're walking from one place to another. You think of yourself as moving through space, covering distance, while time ticks along independently. Space is where you move, time is when you move. They're separate things. You might walk for 10 minutes and cover half a mile. The 10 minutes is time. The half mile is distance. They're measured differently, thought about differently, experienced differently. Time is something you can't control or change. Distance is something you can measure with a ruler or count with your steps. But Einstein realized they're not separate at all. They're intimately connected, woven together into a single four-dimensional structure. This structure is what we call space-time. Think of it this way. To describe when and where something happens, you need four numbers. You need three numbers to specify a location in space: how far north or south, how far east or west, how far up or down. These are your three spatial dimensions, and you need one number to specify when it happens in time. That's your fourth dimension. In Newtonian physics, these four numbers are independent. You can change where something is without changing when it is. You can change when something happens without changing where it happens. Space and time are separate. But in Einstein's physics, these four dimensions aren't independent. They're mixed together. How you move through space affects how you move through time. Your motion through one dimension affects your motion through the others. You can't separate them cleanly. They're intertwined. Here's a helpful way to visualize it, though like all analogies, this one has limits. Imagine space-time as a fabric stretched out in all directions. Everything in the universe exists within this fabric. Every object, every particle of light, every bit of matter and energy is embedded in space-time, moving through it. This fabric has four dimensions instead of the two dimensions of an actual piece of cloth. But the basic idea is the same. It's a structure, a framework, within which everything exists and moves. But here's the crucial part. You're always moving through space-time at a constant rate. Always. Even when you're sitting perfectly still, you're moving through time. Every second you advance 1 second into the future, you're moving through the time dimension of space-time. Now, when you start moving through space, you're essentially redirecting some of your motion through space-time from the time direction into a space direction. It's like tilting your direction of travel. Instead of moving purely through time, you're now moving through a combination of time and space. And here's where it gets interesting. The faster you move through space, the slower you move through time. Your total motion through space-time stays constant, but it gets redistributed between space and time. Imagine you're walking north at a steady pace. Then you decide to also walk east at the same time. Your total speed hasn't changed, but now that speed is divided between northward motion and eastward motion. You're moving north more slowly than before because some of your motion is now directed east. Similarly, when you move through space, you're redirecting some of your motion through space-time away from the time direction and into a space direction. This means you're moving through time more slowly. Time, for you, passes more slowly than it does for someone who isn't moving through space. This isn't a metaphor. This isn't a convenient way of talking about complex mathematics. This is literally how the universe works, and it has consequences that are measurable, testable, and confirmed by countless experiments. The mathematics of spacetime was developed further by one of Einstein's former professors, Hermann Minkowski. Minkowski showed that Einstein's special relativity could be understood geometrically as the geometry of a four-dimensional spacetime. He famously declared, "Henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality." In Minkowski's spacetime, events are points. The history of an object is a curve through spacetime, called a world line, and the separation between events is measured not by distance alone or time alone, but by a quantity called the spacetime interval that combines both. This spacetime interval is what all observers agree on, even when they disagree about distances and times separately. It's an invariant, a fixed property of spacetime geometry that doesn't depend on your motion. Think of it this way. If two people measure the distance between two cities, and one person measures it going north-south, while another measures it going east-west, they'll get different numbers. But they can both calculate the straight-line distance using the Pythagorean theorem, and they'll agree on that. Similarly, different observers moving at different speeds will measure different spatial distances and different time intervals between two events. But they can all calculate the space-time interval, and they'll all get the same answer. This is the deep structure of space-time. Beneath the observer-dependent measurements of space and time, there's an objective geometry that all observers share. Before we go further into the consequences of space-time, we need to understand something fundamental about light itself. Because light isn't just fast, it's special in a way that nothing else in the universe is. The speed of light in empty space is about 186,000 miles per second, or about 300 million meters per second, or about 670 million miles per hour. Let's sit with this number for a moment and really appreciate how fast it is. Light can circle the entire Earth more than 7 times in a single second. If you could somehow see a flash of light traveling around the equator, it would lap the planet over and over again in the time it takes you to blink. Light can travel from the Sun to Earth in about 8 minutes and 20 seconds. The Sun is about 93 million miles away, and light covers that vast distance in less time than it takes to cook breakfast. Light from the nearest star beyond our Sun, Proxima Centauri, takes about 4.2 years to reach us. Light from the center of our Milky Way galaxy takes about 26,000 years. Light from the Andromeda Galaxy, our nearest large galactic neighbor, takes about 2.5 million years. When we look at distant galaxies through telescopes, we're seeing them as they were billions of years ago, because that's how long their light has taken to reach us. So yes, light is extraordinarily fast by any everyday standard. But the speed isn't what makes light special. What makes light special is that its speed is the same for everyone, no matter how they're moving. Think about how speed normally works. If you're standing still and someone drives past you at 50 miles per hour, you measure their speed as 50 miles per hour. But if you're in a car driving at 30 miles per hour in the same direction, you'd measure the other car's speed relative to you as only 20 miles per hour. If you were driving at 50 miles per hour in the same direction, the other car would appear stationary relative to you. This is common sense. Speeds add and subtract, depending on your motion. Velocity is relative. It depends on who's measuring. But light doesn't behave this way. If you're standing still and you measure the speed of a beam of light, you get about 186,000 miles per second. Now imagine you get in a spacecraft and accelerate to half the speed of light, about 93,000 miles per second. Then measure the speed of that same beam of light. You might expect it to appear slower. If it was moving toward you, you might expect to measure it going about 232,000 miles per second, the original speed plus your speed. If it was moving away from you, you might expect to measure about 93,000 miles per second, the original speed minus your speed. But you don't. No matter how fast you're going, no matter which direction you're moving, you still measure that light traveling at exactly 186,000 miles per second. This is bizarre. It violates our intuition about how motion should work. It seems mathematically impossible, but it's been confirmed by countless experiments with increasing precision for more than a century. The Michelson-Morley experiment we discussed earlier was an early confirmation. Since then, particle accelerators have accelerated electrons to more than 99.999999% of the speed of light. And even at those speeds, when those electrons emit light, that light travels at exactly the speed of light, relative to the electrons, and also relative to the stationary laboratory. The speed of light is a cosmic speed limit, a fixed feature of the universe that never changes no matter what. And it's this fact, this strange invariance of the speed of light, that forced Einstein to rethink space and time. Because if the speed of light is the same for everyone, then the only way to make that work is for space and time themselves to be flexible, to adjust and change depending on your motion. Think about it. Speed is distance divided by time. If the speed has to stay the same, but you're moving, then distance and time must change in exactly the right way to keep the ratio constant. When you move very fast, distances appear shorter in the direction you're moving. This is length contraction, and time slows down for you. These two effects work together in exactly the right way to ensure that you always measure light traveling at the same speed. This leads to another strange implication. Nothing with mass can ever reach the speed of light. You can accelerate faster and faster, getting closer and closer, but you can never quite get there. As you approach the speed of light, time dilation becomes more and more extreme. Time would nearly stop for you relative to the outside universe, and the energy required to accelerate you further grows without limit. According to Einstein's equations, it would take infinite energy to accelerate an object with mass to the speed of light. Infinite energy doesn't exist, so objects with mass can never reach light speed. Light itself travels at light speed because photons, the particles of light, have no mass at all. They're pure energy, traveling through space-time as waves in the electromagnetic field. And they're always moving at exactly the speed of light, never faster, never slower. From the moment a photon is created to the moment it's absorbed, it travels at light speed. It can never be at rest. It can never speed up or slow down. The speed of light isn't just the speed at which light happens to travel. It's a fundamental property of space-time itself. In fact, physicists sometimes call it the speed of space-time rather than the speed of light. It's the maximum speed at which any information or influence can travel through the universe. It's the speed at which causality propagates, the speed at which cause and effect can spread from one place to another. This cosmic speed limit has profound implications. It means that distant parts of the universe can't instantly affect each other. It means there's a limit to how quickly information can travel. It means that simultaneity, the concept of things happening at the same time, becomes fuzzy and observer-dependent for events separated by large distances. The speed of light connects space and time. It's the conversion factor between spatial distance and temporal duration in the geometry of space-time. And it's woven into the very fabric of reality. When your clock runs slower than mine, let's think about what it means for time to pass at different rates for different people. This is one of the most striking predictions of Einstein's theory, and it's been confirmed so thoroughly that we now take it for granted in many technologies. Imagine two twins. We'll call them Anna and Marcus. They're born at the same moment, in the same place. They grow up together, celebrating birthdays on the same day, aging at the same rate as twins do. Then, when they're 25 years old, Anna decides to take a journey. She boards a spacecraft that can travel at incredibly high speeds, close to the speed of light. Marcus stays home on Earth. Anna's spacecraft accelerates, reaching 90% of the speed of light. It travels out into space for what feels to Anna like a year. Then it turns around and comes back, taking another year from her perspective. So Anna experiences 2 years of travel before returning home. But when she steps out of the spacecraft and reunites with Marcus, something shocking has happened. Marcus has aged. He looks older. Lines have appeared on his face. His hair has started to gray. And when they compare notes, they discover that 10 years have passed for Marcus on Earth, while only 2 years have passed for Anna on the spacecraft. This isn't science fiction. This is a real effect, predicted by Einstein's theory and confirmed by experiment. It's called time dilation, and it's a direct consequence of the geometry of spacetime. The reason it happens goes back to what we discussed in the previous section. Anna, traveling at high speed through space, has redirected much of her motion through spacetime into the space direction. Less of her motion is directed through time. So, from the perspective of spacetime, time passes more slowly for her. Think of it in terms of the total motion through spacetime. Both Anna and Marcus are always moving through spacetime at the same total rate. But Marcus, sitting still on Earth, is moving almost entirely through the time dimension. All of his motion through spacetime is directed into the future. Anna, moving at 90% of the speed of light, has redirected a huge fraction of her motion through spacetime into the spatial dimensions. Less of her motion is available for the time dimension. So she ages more slowly. Her clocks tick more slowly. Her biological processes happen more slowly. Everything about her experience of time is slowed down relative to Marcus. But here's the strange part. From Anna's perspective during the journey, everything feels completely normal. She doesn't feel time moving slowly. She doesn't feel like she's in slow motion. She eats meals, sleeps, reads books, and everything seems to happen at a normal rate. Her heartbeat feels normal. Her thoughts unfold at a normal pace. If she has a clock with her, it ticks away seconds at what seems like a perfectly regular rate. It's only when she compares her experience with Marcus's experience that the difference becomes apparent. She's experienced 2 years. He's experienced 10. Both measurements are correct. Both clocks were working perfectly. Time itself genuinely passed at different rates. This has been tested in the real world many times with increasing precision. In 1971, physicists Joseph Hafele and Richard Keating performed a famous experiment. They took 4 cesium atomic clocks, some of the most precise timekeeping devices available, on commercial airplane flights around the world. Some clocks flew eastward, in the direction of Earth's rotation. Others flew westward, against Earth's rotation. When the clocks returned, and were compared to identical atomic clocks that had stayed at the United States Naval Observatory in Washington, the flying clocks had measured slightly less time passing. The difference was tiny, just a few hundred billionths of a second, because airplanes are slow compared to the speed of light. But the difference was there, exactly as Einstein predicted. The eastward flying clocks lost about 59 nanoseconds compared to the ground clocks. The westward flying clocks gained about 273 nanoseconds. The asymmetry comes from Earth's rotation, which means eastward flying clocks are moving faster relative to the center of Earth than westward flying clocks. Astronauts on the International Space Station experience the same effect. The station orbits at about 17,500 miles per hour, which is fast by everyday standards, but still only about 0.0025% of the speed of light. At that speed, time dilation is real, but small. After 6 months in space, an astronaut ages about 0.005 seconds less than they would have on Earth. Not much, but measurable with precise instruments. If you could somehow spend your entire life on the space station, by the time you were 80 years old, you'd be about zero point 0.8 seconds younger than if you'd spent your life on Earth's surface. Now imagine if we could build a spacecraft that travels at 90% of the speed of light, like in our thought experiment with Anna and Marcus. At that speed, the time dilation factor is about 2.3. This means for every year that passes on the spacecraft, more than 2 years pass on Earth. At 99% of the speed of light, 1 year on the ship equals more than 7 years on Earth. At 99.9% of the speed of light, 1 year equals more than 22 years on Earth. And this effect becomes more and more extreme as you approach the speed of light. At 99.999% of the speed of light, 1 year on the ship would equal more than 700 years on Earth. This is why we say the speed of light is a cosmic speed limit. You can never quite reach it if you have mass. As you get closer and closer, time dilation becomes more and more extreme. From the perspective of the outside universe, you would appear to move in increasingly slow motion, asymptotically approaching, but never reaching the speed of light. And the energy required to accelerate you further grows without limit, approaching infinity as you approach light speed. But light itself, photons, particles of pure energy with no mass, always travel at exactly the speed of light. From the perspective of a photon, if such a perspective makes sense, time doesn't pass at all. A photon emitted from a distant star billions of light years away and arriving at your eye right now has, in a sense, experienced no time at all during its journey. From its perspective, emission and absorption are the same moment. This isn't a trick or an illusion. Both clocks in our thought experiment are working perfectly. Both are measuring time accurately. Time itself is genuinely passing at different rates. Think about what this means. Time, the thing that feels most constant and universal in our everyday lives, the thing that seems to flow the same for everyone, isn't universal at all. It's personal. It depends on how you're moving through space-time. Your time is your own, and someone moving differently through the universe experiences a different flow of time, equally real, equally valid. We've talked about how time changes depending on motion, but that's only half the story. Space changes too, and in a way that's intimately connected to the changes in time. Imagine you're on that same spacecraft, traveling at 90% of the speed of light. From your perspective on the ship, you're not moving at all. You're sitting in your chair looking out the window. It's the universe outside that's moving, rushing past you at 90% of light speed. And as it does, something strange happens to the distances you measure. The space between objects in the direction you're traveling appears compressed, shortened, squeezed together. A distance that someone on Earth measures as 100 miles might appear to you as only about 44 miles. This is called length contraction, and like time dilation, it's a real effect predicted by special relativity and confirmed by observation. Think about what this means. You and someone on Earth are looking at the same region of space, but you measure it as having a different length. The meter stick you're using works perfectly well. The meter stick the person on Earth is using works perfectly well, but you get different answers. Who's right? Both of you are. Space itself, the distance between things, changes depending on how you're moving through space-time. There's no absolute objective distance that everyone agrees on. Distance is relative, just like time. This might seem even stranger than time dilation. At least with time, we have some experience of it, feeling like it passes quickly or slowly in different situations, even if that's just psychological. But distance seems like the most concrete physical thing imaginable. How can the space between two objects change depending on who's measuring? The answer lies again in space-time. Space and time aren't separate. They're mixed together, and they're mixed differently for different observers. When you move very fast through space, you're not just changing your position. You're changing your orientation in space-time, your angle through the four-dimensional structure. And from that different angle, distances in space appear different, just as time intervals appear different. Here's an analogy that might help. Though, like all analogies for relativity, it's imperfect. Imagine you're looking at a rectangular piece of paper straight on. You measure its width and height. Now tilt the paper at an angle, rotating it in three-dimensional space. From your new perspective, the width appears shorter. The paper itself hasn't changed, but your view of it has. What you're seeing is a projection of the three-dimensional object onto your two-dimensional field of view. Similarly, when you're moving through space-time, your perspective on space and time changes. What you measure as a distance in space and what you measure as a duration in time are projections of the four-dimensional space-time structure onto your three-dimensional space and one-dimensional time. Different observers, moving differently, make different projections. The mathematics of length contraction is precisely connected to time dilation. In fact, they're two aspects of the same phenomenon, two different manifestations of the geometry of space-time. At everyday speeds, length contraction is completely negligible. Even at the speed of a jet airplane, about 500 miles per hour, the contraction factor is about 1 part in 10 trillion. You would need measuring instruments, far more precise than anything that currently exists to detect it. But at speeds approaching light speed, the effect becomes dramatic. At 90% of light speed lengths, in the direction of motion, contract to about 44% of their rest length. At 99% of light speed, they contract to about 14%. At 99.9%, to about 4.5%. This has been observed indirectly in particle accelerators. When particles are accelerated to speeds very close to light speed, their apparent size in the direction of motion, as measured by how they interact with other particles, is consistent with length contraction. There's a famous thought experiment called the ladder paradox that illustrates how strange length contraction can be. Imagine a ladder that's too long to fit in a garage when both are at rest. But if you run toward the garage carrying the ladder at a high enough speed, the ladder contracts in length, and from the garage's perspective, it fits inside, at least for a moment. But here's the paradox. From the ladder's perspective, it's the garage that's moving, and the garage contracts, becoming even shorter. From the ladder's perspective, there's no way it could possibly fit. The resolution involves careful thinking about simultaneity, about what it means for the front and back of the ladder to be in the garage at the same time. Different observers have different notions of simultaneity, and when you account for that properly, the paradox resolves. Both perspectives are consistent with each other when you think carefully about the geometry of space-time. This leads to something truly strange. Two observers moving differently through space can disagree about distances, disagree about time intervals, disagree about whether two events happened at the same time, and both be completely correct. There's no absolute answer to how far apart two things are, or how much time passed between two events, or whether two events were simultaneous. The answer depends on who's measuring. And yet, despite all this flexibility, despite all this observer dependence, there are things that stay constant. The speed of light is one. Another is the space-time interval, a mathematical combination of space and time that all observers agree on, even when they disagree about space and time separately. The space-time interval is like the invariant distance in ordinary space. If two people measure the east-west and north-south distances between two cities differently because they're using rotated coordinate systems, they'll still agree on the straight-line distance between the cities. Similarly, observers in different states of motion will measure different spatial and temporal separations between events, but they'll all agree on the space-time interval. This invariant structure, this objective geometry of space-time that all observers share despite their different perspectives, is what gives relativity its power and consistency. The relativity of now. Let's think more carefully about what it means for different observers to experience reality differently. because this is where special relativity starts to challenge our deepest assumptions about the nature of existence. Imagine three people. One is standing still on Earth, another is on a spacecraft, traveling east at half the speed of light. A third is on a different spacecraft, traveling west at half the speed of light. Two events happen somewhere out in space. Maybe two stars explode as supernovae. These explosions are far enough apart that light from one explosion can't reach the location of the other before it explodes. The events are causally disconnected, meaning neither could have caused the other. The question is, which one exploded first? You might think this question has a simple, definitive answer. Either star A exploded first, or star B exploded first, or they exploded at the same time, and everyone in the universe should agree on which it was, right? But that's not how space-time works. The person standing still on Earth might carefully measure the light from both explosions, account for light travel times, and conclude that star A exploded first, say 100 years before star B. The person traveling east at half-light speed might do the same calculations from their reference frame and conclude that star B exploded first, 50 years before star A. The person traveling west might conclude that the two explosions were perfectly simultaneous, happening at exactly the same moment. And here's the crucial part. All three observers are correct. There is no objective fact of the matter about which explosion happened first. The time ordering of these two events is not an absolute property of reality. It depends on your motion through space-time. This isn't a matter of communication delays or light travel times. This isn't about how long it takes information to reach different observers. This is about the fundamental nature of simultaneity, the concept of two things happening at the same time. In Newtonian physics, simultaneity is absolute. If two events happen at the same time, they happen at the same time for everyone, everywhere in the universe. There's a universal present moment, a cosmic now, that all observers share. In Einstein's space-time, simultaneity is relative. Events that are simultaneous for one observer can happen in a different order for another observer. Time order is not universal for events that are causally disconnected. Now, there are limits to this. If two events are connected in a way that one could have caused the other, then all observers will agree on their order. If you see a light turn on and then see it turn off, every observer in the universe will agree that the light turned on first and off second, even if they disagree about how much time passed between the two events. This makes sense from a causality perspective. If event A causes event B, then A must happen before B for everyone. Otherwise, you could have contradictions, situations where some observers see effects preceding their causes. The mathematics ensures this works out. Events that can influence each other, that are connected by signals traveling at or below the speed of light, have an absolute time order that all observers agree on. But for events that are too far apart in space and too close together in time to have influenced each other, the time order can be different for different observers. Think about what this means for reality. The idea that there's a single present moment, a single now, that extends across the entire universe, is an illusion. There is no cosmic present. There is no universal flow of time carrying everything forward together. Instead, there are countless different definitions of now, one for each possible state of motion. Your now includes events that are in my past or my future. My now includes events that are in your past or your future. We slice space-time into space and time differently, and both slicings are equally valid. This is one of the deepest insights of relativity. There is no objective, universal reality that exists independently of observers. Reality is always reality from a perspective, from a particular motion, through space-time. But this doesn't mean reality is purely subjective, that anything goes, that everyone can believe whatever they want and all beliefs are equally true. There are still objective facts. The world lines of particles through space-time are objective. Whether two events can causally influence each other is objective. The laws of physics are objective. What's observer-dependent is the division of space-time into space and time, the determination of what's happening now versus what happened in the past or will happen in the future. The when and where of events, for events that can't causally influence each other, are relative. This is subtle, but important. Relativity doesn't say that truth is relative or that reality is whatever you think it is. It says that certain concepts we thought were absolute, like simultaneity and the present moment, are actually relative. But there's still an objective space-time structure that all observers share, and objective laws of physics that govern how things move through that structure. Different observers just slice that objective structure in different ways. Let's pause here for a moment and let that sink in. We've established something profound. Time is not the same for everyone. It's not a universal river carrying us all downstream together. It's more like a personal experience, shaped by how you move through the universe. Space is not fixed either. Distances change depending on your motion. What you measure as a meter might be measured as something different by someone moving at a different speed. And simultaneity, the concept of things happening at the same time, is relative. Your now is not my now if we're moving differently through space. This contradicts everything our intuition tells us. In our everyday lives, time feels absolute. We synchronize our watches. We agree on when things happen. We all age at the same rate as the people around us. And for the most part, that's true, because we're all moving very slowly compared to the speed of light. The differences in how time passes for people on Earth are incredibly tiny, whether you spend your life sitting still or constantly traveling in airplanes. The difference in how much you age is measured in millionths of a second. For all practical purposes in daily life, time is universal. But the principle matters. The fact that time can pass at different rates, even if the effect is usually negligible, tells us something fundamental about the nature of reality. Slow down your thoughts for a moment and really consider what this means. The universe doesn't have a single, universal clock. There's no cosmic timepiece ticking away, defining the present moment for everyone, everywhere. Instead, every observer carries their own time, their own sense of now, and these different times are all equally real, all equally valid. This is one of those ideas that seems simple when stated, but becomes more and more strange the more you think about it. Your now is not my now if we're moving differently through space. Your future might be my past. Your past might be my future. And both of our perspectives are equally correct. There's no objective answer to the question, what time is it? The answer depends on who's asking, on how they're moving through space-time. This is just the beginning of the strangeness. We're going to go deeper. We're going to explore not just how motion affects time and space, but how mass and gravity reshape the very fabric of space-time itself. We're going to discover that space-time can curve, that this curvature is what we experience as gravity. But for now, let this idea settle in your mind. Space and time are woven together into space-time. They're flexible, changing depending on motion. And your experience of reality depends on how you're moving through this four-dimensional structure. Take a moment. Breathe. Let your mind adjust to this new way of thinking about space and time. It's okay if it feels strange. It should feel strange. We're stepping outside the familiar and into territory that defies our everyday intuition. But we're doing it carefully, one step at a time, building understanding slowly and steadily. Gravity as the shape of space-time. So far, we've been talking about special relativity, Einstein's theory of how space and time work for objects moving at constant speeds through empty space, far from any sources of gravity. But Einstein didn't stop there. He spent another 10 years, from 1905 to 1915, working on a deeper question. What happens when objects accelerate? And what is gravity, really? The answer he found was even more revolutionary than special relativity. It's called general relativity, and it reveals that space-time isn't just flexible in how we divide it into space and time. Space-time itself can bend and curve. Its geometry can change. And this curvature is what we experience as gravity. To understand this, we need to think about gravity in a completely new way. Newton described gravity as a force, an attraction between massive objects. Earth pulls on the moon pulls on Earth, the sun pulls on the planets, and so on. This gravitational force reaches across empty space, pulling objects together. But Einstein realized that gravity isn't a force at all. It's a consequence of the curvature of spacetime. Mass and energy cause spacetime to curve, to bend, to warp, and objects moving through curved spacetime naturally follow curved paths. What we experience as the force of gravity is actually just the geometry of spacetime. This is such a radical idea that it's worth sitting with for a moment. Einstein is saying that gravity, the phenomenon that seems so obviously like a force pulling you down toward the ground, isn't a force at all. There's nothing pulling on you. Instead, the mass of Earth has curved the spacetime around it, and you're simply following the natural geometry of that curved spacetime. Imagine a large sheet of stretchy fabric pulled tight. If you place a heavy ball in the middle of the sheet, it creates a dip, a depression, a curved region. The fabric bends around the ball. Now, if you roll a smaller ball across the sheet, it won't travel in a straight line. It will curve toward the heavy ball, falling into the depression. This is a common analogy for how gravity works in general relativity. Massive objects curve spacetime around them, and other objects follow the curves. The smaller ball isn't being pulled by a force. It's just following the natural path through the curved geometry of the fabric. But this analogy has significant limitations. For one thing, it makes it seem like gravity is pulling things down, when really there's no down in space. The fabric in the analogy appears to curve downward because of Earth's gravity in our everyday experience, but that's not part of the space-time geometry itself. More importantly, the fabric in the analogy is two-dimensional, representing only two of space's three dimensions. Real space-time is four-dimensional, three of space, and one of time. The curvature happens in all four dimensions, including time. In fact, the curvature of time is what creates most of the gravitational effects we experience in everyday life. Earth's mass causes time to pass slightly more slowly near Earth's surface than it does far away in empty space. This gradient, this change in the rate of time flow, creates what we experience as gravitational attraction. Think about it this way. If you're in free fall, floating in space with nothing supporting you, you're not being pulled by a force. You're simply moving through curved space-time, following what's called a geodesic, the straightest possible path through a curved space. A geodesic is the path an object follows when no forces act on it. In flat space-time, geodesics are straight lines, but in curved space-time, geodesics are curved. They bend and wind through the four-dimensional geometry. When you jump off a diving board, you're in free fall. You feel weightless. From your perspective, you're not experiencing any forces. You're just floating, following a natural path through space-time. It's only when you hit the water, when the water exerts a force to stop your fall, that you feel the force again. Einstein described this beautifully. Objects in free fall, whether it's a satellite orbiting Earth or an apple falling from a tree, or an astronaut floating in a space station, are actually moving in straight lines through curved spacetime. They're following geodesics, the straightest possible paths through a curved four-dimensional geometry. What we call gravity is just spacetime curvature. The bending of paths, the acceleration of falling objects, the orbits of planets, all of it emerges naturally from the geometry of curved spacetime. This was Einstein's great insight. Gravity is geometry. Mass tells spacetime how to curve, and spacetime tells matter how to move, proving Einstein right. When Einstein first proposed that gravity was curved spacetime rather than a force, it sounded like wild speculation, like philosophy rather than physics. But Einstein was able to make specific, testable predictions based on his theory. And those predictions have been confirmed again and again with increasing precision. One of the first tests came in 1919, just a few years after Einstein published general relativity. The prediction involved something that Newton's theory of gravity could not explain: the bending of light by gravity. In Newton's theory, light has no mass, so gravity shouldn't affect it. Light should travel in straight lines, unaffected by the gravitational pull of massive objects. But in Einstein's theory, light follows geodesics through curved spacetime, just like everything else. And if spacetime is curved by a massive object, those geodesics are curved, which means light paths are curved. Light bends around massive objects. Einstein calculated exactly how much light from a distant star should bend as it passes near the sun. During a total solar eclipse, when the sun's light is blocked by the moon, stars that appear close to the sun in the sky become visible. Einstein predicted that these stars would appear slightly shifted from their normal positions because their light was being bent by the sun's gravity. The effect is tiny, less than 2 seconds of arc, about the angular size of a coin seen from 2 miles away. But it's measurable with careful observations. On May 29, 1919, there was a total solar eclipse visible from parts of South America and Africa. British astronomer Arthur Eddington led expeditions to both locations to photograph the eclipse and measure the positions of stars near the sun. When the photographs were analyzed and compared to photographs of the same region of sky taken when the sun was elsewhere, the stars appeared shifted by almost exactly the amount Einstein predicted. Light does bend around massive objects. Space-time is curved. This result made Einstein an international celebrity overnight. The London Times ran the headline, "Revolution in Science, New Theory of the Universe, Newtonian Ideas Overthrown." Here was experimental proof that our understanding of space, time, and gravity had fundamentally changed. Since then, we found countless other confirmations of general relativity's predictions. We've observed light from distant galaxies being bent and magnified by the gravity of galaxy clusters in between, an effect called gravitational lensing. The massive cluster acts like a giant lens, bending light from more distant objects. Sometimes, this creates multiple images of the same background galaxy, or it distorts the galaxy into arcs and rings. Gravitational lensing has become a powerful tool in astronomy. It allows us to study very distant galaxies that would otherwise be too faint to see. It lets us map the distribution of dark matter in galaxy clusters, and it provides constant confirmation that gravity really does curve spacetime and bend light. We've measured how planets orbit the sun with a precision that matches general relativity's predictions perfectly. Mercury, the innermost planet, has an orbit that slowly precesses, shifting over time. Newton's theory couldn't fully explain this precession. There was a tiny discrepancy, just 43 seconds of arc per century, that remained unexplained. General relativity predicts this precession exactly, as a natural consequence of space-time curvature near the sun. We've detected gravitational waves, ripples in space-time itself created by violent cosmic events, like colliding black holes and neutron stars. We'll talk more about these later, but they're direct evidence that space-time is a real, physical thing that can wave and ripple. But one of the most striking confirmations of curved space-time, one that affects your life every single day, comes from something you probably use regularly: GPS, the Global Positioning System. GPS works by using satellites orbiting Earth to triangulate your position. These satellites carry extremely precise atomic clocks that broadcast time signals. Your GPS receiver picks up signals from multiple satellites, compares the times, and calculates how far you are from each satellite based on how long the signals took to reach you. With signals from at least 4 satellites, the system can determine your position to within a few meters. But those clocks on the satellites are moving relative to people on Earth's surface, and they're farther from Earth's mass. Both of these effects influence how time passes on the satellites, according to relativity. The satellites are moving at about 14,000 kilometers per hour, or about 8,600 miles per hour, relative to Earth's surface. According to special relativity, moving clocks tick slower, so the satellite clocks should run slow compared to clocks on the ground. This would cause an error of about 7 microseconds per day. But the satellites are also about 20,000 kilometers, or about 12,400 miles, above Earth's surface, where gravity is weaker. According to general relativity, clocks tick faster in weaker gravitational fields, so the satellite clocks should run fast compared to ground clocks. This would cause an error of about 45 microseconds per day. The two effects work in opposite directions, but they don't cancel out completely. The gravitational time dilation effect is larger. Overall, the satellite clocks run about 38 microseconds per day, faster than identical clocks on Earth's surface. This might not sound like much, but GPS calculations depend on incredibly precise timing. Light travels about 30 centimeters, or about 1 foot, in 1 nanosecond. A timing error of 38 microseconds per day would cause position errors of about 10 kilometers, or about 6 miles per day. Within a few hours, GPS would be completely useless. But GPS engineers knew about relativity when they designed the system. The satellite clocks are deliberately set to tick at a slightly different rate than Earth clocks, accounting for both special and general relativistic effects. As a result, when the satellites are in orbit, their clocks stay synchronized with ground clocks to within a few billionths of a second. The fact that GPS works so precisely is a constant, everyday confirmation that Einstein was right about spacetime. Time really does pass at different rates, depending on both motion and gravity. Space really is curved by mass, and we have to account for these effects to navigate our world. Every time you use GPS to find your way to a destination, you're relying on the truth of general relativity. You're using technology that depends on the curvature of spacetime. Let's think more carefully about how gravity affects time, because this might be the strangest aspect of curved spacetime. We touched on it briefly, but it deserves deeper exploration. Imagine you're standing at the bottom of a tall tower, and your friend is at the top. You both have identical, perfectly synchronized atomic clocks. According to general relativity, time passes more slowly for you at the bottom than it does for your friend at the top, because you're deeper in Earth's gravitational field, closer to Earth's center of mass, where space-time is more curved. The effect is tiny for ordinary towers. For a tower 100 meters, or about 330 feet tall, the clock at the top would gain about 1 nanosecond per day compared to the clock at the bottom. For a tower a kilometer tall, about 10 nanoseconds per day. These are incredibly small differences, but with sensitive enough instruments, we can measure them, and we have. In 1971, physicists at the National Bureau of Standards, now called the National Institute of Standards and Technology, measured the gravitational time dilation between two atomic clocks, separated by just 2 meters, about 6.5 feet, of vertical height. The difference in tick rates was about 46 parts in 1 quintillion, an almost incomprehensibly small fraction. But it was there, and it matched general relativity's prediction. In more recent years, optical atomic clocks have become so precise that they can measure gravitational time dilation over height differences of just a few centimeters. Raise a clock by 1 foot, and time speeds up by about 90 parts in 1 quintillion. This has practical implications. If you want to synchronize atomic clocks to the highest precision, you need to account for their heights above sea level. A clock in a basement runs slower than a clock on an upper floor of the same building. Now imagine something more extreme. Imagine you could stand on the surface of a neutron star, one of the densest objects in the universe. A neutron star packs about 1.5 times the mass of our Sun into a sphere only about 12 miles across. The gravity at the surface is almost incomprehensibly strong, about 200 billion times stronger than Earth's surface gravity. If you stood on a neutron star with a clock, and someone observed you from far away in flat spacetime, they would see your clock ticking much more slowly than their own. Time dilation would be extreme. Every second on your clock might correspond to several seconds on theirs. Of course, you couldn't actually stand on a neutron star. The gravity would instantly crush you into a thin layer of exotic matter. But hypothetically, if you could somehow survive and spend what feels to you like a year on that neutron star, then return to normal space, you would have aged far less than people who stayed away from the intense gravity. This is gravitational time dilation, and it's every bit as real as the time dilation from motion that we discussed earlier. In fact, the two types of time dilation are intimately connected. They're both manifestations of space-time curvature, different aspects of the same underlying geometry. White dwarfs, the dense remnants of stars like our Sun, also create measurable gravitational time dilation. Light emitted from the surface of a white dwarf is shifted toward lower frequencies, toward the red end of the spectrum, because the light climbs out of the star's gravitational well and loses energy in the process. This gravitational redshift has been measured for several white dwarfs, confirming general relativity's predictions. And there's an even more extreme case we need to talk about: black holes, where light cannot escape. A black hole is a region of spacetime where gravity is so strong that nothing, not even light, can escape from inside a certain boundary. That boundary is called the event horizon, and it marks the point of no return. Black holes form when massive stars collapse at the end of their lives, compressing enormous amounts of matter into incredibly small volumes. For a star about 20 times the mass of our Sun, this could create a black hole with an event horizon about 60 kilometers, or about 37 miles across. Once matter collapses beyond a certain density, nothing can stop it from collapsing further. It creates such intense curvature of space-time that it forms what we call a singularity, a point where the curvature becomes infinite, where our equations break down and can't describe what's happening. Near a black hole, all the strange effects of curved spacetime become extreme and undeniable. Imagine you're watching someone fall toward a black hole from a safe distance. As they get closer to the event horizon, you see them moving more and more slowly. Time dilation becomes more and more extreme. They appear to move in slow motion, getting slower and slower, never quite reaching the horizon from your perspective. Their image becomes dimmer and redder as light struggles to escape the intense gravitational field. The light waves are stretched, shifted toward longer wavelengths. Eventually, they fade from view, frozen at the edge of the event horizon. In fact, from your perspective far away, they never cross the event horizon at all. They appear to asymptotically approach it, getting closer and closer, but never quite arriving, time slowing down more and more, until it appears to stop completely at the horizon. But from their perspective, something entirely different happens. They don't feel themselves slowing down. From their point of view, time passes normally. They cross the event horizon in a finite amount of their own time and continue falling inward. To them, there's nothing special about the event horizon. They pass through it without even noticing, at least at first. This is one of the most unsettling aspects of space-time curvature. Two observers can have radically different experiences of the same event, and both experiences are real. Both are correct. There's no objective answer to when does the person cross the event horizon. From the distant observer's perspective, they never do. From the falling person's perspective, they do. Once past the event horizon, not even light can escape. The curvature of space-time is so extreme that all paths, all possible trajectories, lead inward toward the singularity. There's no direction you can point your rocket engines that would let you escape. It would be like trying to travel backward in time. The geometry simply doesn't allow it. The event horizon isn't a physical surface. It's just a boundary in space-time, a point of no return. But it has remarkable properties. From the outside, the event horizon appears perfectly black. No light comes from it. It's an absolute darkness, a region of space-time from which no information can escape. At the center of a black hole, Einstein's equations predict a singularity, a point where space-time curvature becomes infinite, where density becomes infinite, where our mathematical descriptions stop making sense. We don't really know what happens there. General relativity itself stops working at singularities. The theory predicts its own breakdown. Most physicists believe this indicates that general relativity is incomplete, that we need a deeper theory to understand what happens in these extreme conditions. That deeper theory would likely be a quantum theory of gravity, combining general relativity with quantum mechanics. But we don't yet have such a theory, at least not one that's complete and confirmed by experiment. Despite not fully understanding singularities, we can study black holes. We've observed them indirectly for decades, seeing stars orbit around invisible massive objects at the centers of galaxies, seeing jets of matter being flung out from the regions near black holes, seeing the effects of their intense gravity on surrounding material. And in recent years, we've done something even more remarkable. We've photographed black holes. In April 2019, the Event Horizon Telescope collaboration released the first image of a black hole's shadow. It showed the supermassive black hole at the center of galaxy M87, about 53 million light-years away. The black hole has a mass of about 6.5 billion times the mass of our Sun. The image shows a dark region, the shadow of the event horizon, surrounded by a bright ring of hot gas being pulled toward the black hole. The gas is heated to billions of degrees as it spirals inward, emitting intense radiation. But the event horizon itself is dark, a perfect circle of blackness, where space-time curves so intensely that light cannot escape. This image is direct visual confirmation that black holes exist, that event horizons are real, that general relativity's predictions about extreme space-time curvature are correct. Black holes are real. They exist throughout the universe, and they represent the most extreme curvature of space-time that we know of. Regions where the fabric of reality bends back on itself so intensely that it creates a one-way membrane in space-time, a point of no return. In 2015, almost exactly 100 years after Einstein published general relativity, scientists detected gravitational waves for the first time, directly confirming one of the theory's most dramatic predictions. Gravitational waves are ripples in space-time itself, created when massive objects accelerate violently. They travel at the speed of light, stretching and squeezing space as they pass through. Einstein predicted gravitational waves in 1916, just a year after completing general relativity. He showed that his equations allowed for wave-like solutions, oscillations in the curvature of space-time that could propagate through the universe. But Einstein himself was skeptical about whether they could ever be detected. He calculated that gravitational waves would be incredibly weak. Even waves from the most violent cosmic events would cause only tiny distortions of space by the time they reached Earth. He was almost right. It took decades of technological development to build instruments sensitive enough to detect gravitational waves. The challenge was extraordinary. The waves caused changes in distance smaller than the width of an atomic nucleus across distances of several kilometers. The detection was made by LIGO, the Laser Interferometer Gravitational Wave Observatory. LIGO consists of two identical detectors, one in Louisiana and one in Washington state, each using laser beams traveling along 4-kilometer long, about 2.5-mile long, evacuated tunnels to measure incredibly tiny changes in distance. When a gravitational wave passes through the detector, it briefly changes the length of the tunnels by a minuscule amount. One tunnel might become slightly longer while the perpendicular tunnel becomes slightly shorter. Then they switch. The laser interferometer is sensitive enough to detect these changes, even though they're unimaginably small. On September 14th, 2015, at approximately 5:50 a.m. Eastern Time, gravitational waves from two colliding black holes passed through Earth. These black holes, more than a billion light-years away, had been orbiting each other, gradually spiraling closer and closer together as they radiated energy in the form of gravitational waves. In the final fraction of a second before they merged, they were orbiting each other hundreds of times per second, moving at a significant fraction of the speed of light, creating intense ripples in space-time that propagated outward in all directions. Those ripples, traveling at light speed for more than a billion years, passed through the LIGO detectors. They caused the detector arms to change length by about 1/10,000th the width of a proton. But it was enough. Both LIGO detectors saw the same signal, arriving 7 milliseconds apart, the light travel time between the two sites. The signal matched the predictions of general relativity almost perfectly. By analyzing the waveform, scientists could determine that the black holes had masses of about 20, 9, and 36 times the mass of our Sun, that they merged to form a single black hole of about 62 solar masses, and that about 3 solar masses of energy was radiated away as gravitational waves in the final moments. 3 solar masses worth of energy, E equals mc squared, released in a fraction of a second. For that brief moment, the merger released more power than all the stars in the visible universe combined. And we detected it, felt the ripples in space-time itself passing through our detectors. This detection confirmed one of the last major predictions of general relativity. It showed that space-time really can ripple and wave, that black holes exist and behave as the theory predicts, and that we can detect these waves and use them to study the universe. Since that first detection, LIGO and other gravitational wave observatories have detected dozens more events. Most are from merging black holes, but some are from merging neutron stars. Each detection tells us something about these violent cosmic events, about the behavior of matter and space-time under extreme conditions. In August 2017, LIGO detected gravitational waves from two neutron stars, spiraling together and merging. This time, telescopes around the world also observed light from the event. For the first time, we observed a cosmic event with both gravitational waves and electromagnetic radiation, opening a new era of multi-messenger astronomy. Gravitational waves are also helping us answer fundamental questions about physics. They're allowing us to test general relativity in new ways, in regimes of strong gravity and high speeds that we couldn't access before. So far, every test has confirmed Einstein's theory. They're helping us measure the expansion rate of the universe independently of previous methods, potentially resolving some puzzles in cosmology. They're allowing us to detect black holes that don't emit light and would be invisible to traditional telescopes. And they're a direct demonstration that space-time is a real physical thing that can vibrate and carry energy. Whatever space-time is, it's not just an abstract mathematical framework or a convenient way of describing relationships. It's something that can wave and ripple, something that interacts with matter and energy, something that carries information across the universe. The detection of gravitational waves was a triumph of general relativity, of Einstein's insight that gravity is curved space-time, that mass and energy tells space-time how to curve, and space-time tells mass and energy how to move. It was also a testament to human ingenuity and persistence, the result of decades of effort by thousands of scientists and engineers to build instruments sensitive enough to detect these whispers from the universe. The universe gets bigger. We've been talking about space-time on relatively small scales. The motion of objects, the curvature around stars and planets and black holes. But space-time has one more surprise for us, one that operates on the largest scales imaginable, across the entire observable universe. The universe itself is expanding. This discovery, made in the 1920s and 1930s, was one of the most shocking findings in the history of astronomy. Galaxies throughout the universe are moving away from each other, and the farther away a galaxy is, the faster it's receding. At first, this sounds like it might just be motion through space, galaxies flying away from each other like debris from an explosion. But that's not quite right. It's not that galaxies are moving through space. It's that space itself is expanding, carrying galaxies along with it. Think of it this way. Imagine a balloon with dots painted on its surface to represent galaxies. As you inflate the balloon, the dots move apart from each other. But the dots themselves aren't moving across the surface of the balloon. The surface itself is expanding, stretching, and the dots are being carried along with the expansion. Similarly, space is expanding, and galaxies are being carried apart by that expansion. The distances between galaxies are growing, not because the galaxies are moving through space, but because space itself is growing, stretching, creating more distance between them. This is a prediction of general relativity. Einstein's equations allow for space-time to be dynamic, to expand or contract over time. In fact, Einstein initially found this prediction so strange, so contrary to his intuition, that the universe should be static and unchanging, that he modified his equations to prevent it. He added a term called the cosmological constant to keep the universe from expanding or contracting. But observations showed that the universe really is expanding. In the 1920s, astronomer Edwin Hubble measured the distances to many galaxies and found that distant galaxies are moving away from us. The farther away they are, the faster they're receding. This relationship, now called Hubble's law, was clear evidence of cosmic expansion. When Einstein learned of Hubble's discovery, he removed the cosmological constant from his equations and later called his modification the biggest blunder of his life. The universe was dynamic after all, just as his original equations predicted. The expansion of space has profound implications. If space is expanding now, that means it was smaller in the past. If you run the expansion backward in time, you find that the universe was once incredibly small and dense. This realization led to the Big Bang theory, the idea that the universe began from an extremely hot, dense state about 13.8 billion years ago. In the earliest moments, all the matter and energy in the observable universe was compressed into an unimaginably small volume. Then space began expanding, carrying that matter and energy along with it, cooling as it expanded. The Big Bang wasn't an explosion in space. It was an expansion of space itself. There was no pre-existing space that the universe expanded into. Space itself came into being and has been expanding ever since. We have multiple lines of evidence for this. We can see the afterglow of the Big Bang in the cosmic microwave background radiation, a faint glow that fills the entire sky, the cooled remnant of the intense heat from the early universe. We can measure the abundances of light elements like hydrogen and helium and lithium, which match the predictions of Big Bang nucleosynthesis, the formation of elements in the first few minutes after the Big Bang. And we can observe the large-scale structure of the universe, the distribution of galaxies, which matches predictions based on the expansion of space from a nearly uniform initial state. But here's where it gets even stranger. The expansion of space isn't just continuing. In the late 1990s, astronomers discovered that the expansion is accelerating. Distant galaxies are moving away from us faster and faster, not slower as you might expect if gravity were pulling everything together. This acceleration implies the existence of something called dark energy, a mysterious form of energy that permeates all of space and drives the expansion. We don't know what dark energy is. It might be Einstein's cosmological constant after all, Not a blunder, but a real property of space itself. It might be something else entirely, some exotic field or energy that we don't yet understand. But whatever it is, it makes up about 68% of all the energy in the universe. Dark matter, another mysterious component we can detect through its gravitational effects but haven't directly observed, makes up about 27%. All the ordinary matter, everything made of atoms, everything we can see and touch, makes up only about 5% of the universe's total energy content. The universe is mostly made of things we don't understand, and the expansion of space, driven by dark energy, is carrying it all apart. This expansion creates strange effects. Light traveling from distant galaxies to us is stretched as space expands during its journey. This stretches the wavelengths of light, shifting it toward the red end of the spectrum, an effect called cosmological redshift. The farther away a galaxy is, the more its light is redshifted, and the faster space is expanding between us and it. For very distant galaxies, the redshift can be extreme. Some galaxies we observe have redshifts greater than 10, meaning their light has been stretched to more than 11 times its original wavelength. There's a distance, called the cosmic horizon, beyond which galaxies are receding from us faster than the speed of light. This doesn't violate relativity, because the galaxies aren't moving through space faster than light. Space itself is expanding between us, carrying them along. We can never see beyond this horizon, because light from those regions can never reach us. The expansion of space carries the light away faster than it can travel toward us. In a very real sense, the observable universe has an edge, not because space ends there, but because the expansion of space-time prevents us from seeing farther. And in the distant future, as the expansion continues to accelerate, more and more galaxies will cross this horizon and disappear from our view. Eventually, trillions of years from now, observers in our galaxy will see a universe that appears almost empty, with only our local cluster of gravitationally bound galaxies visible, while the rest of the universe has been carried beyond our reach by the expanding space. Space-time is not static. It's dynamic, evolving, expanding. And this expansion is reshaping the universe on the largest scales, determining the ultimate fate of everything we can see. Let's pause again and take stock of where we are. We started with the simple idea that space and time are woven together into spacetime. We've seen that motion through space affects the flow of time, and that time dilation and length contraction are real effects that have been measured and confirmed. We've discovered that distances aren't fixed, that simultaneity isn't universal, that reality looks different from different perspectives, and that all these different perspectives are equally valid. And now we've learned that space-time isn't just flexible in how we divide it into space and time. The fabric of space-time itself can curve. Massive objects warp the geometry of reality around them. This curvature is what we experience as gravity. And in extreme cases, like black holes, space-time can be curved so intensely that it creates regions from which nothing can escape. We've seen that space-time can ripple with gravitational waves, carrying energy across the universe. And we've discovered that space itself is expanding, carrying galaxies apart, driven by mysterious dark energy. These aren't abstract mathematical ideas. They're real physical effects that have been measured and confirmed. We use them to make GPS work. We observe them in the behavior of planets and stars. We photographed them in the shadows of black holes. We've detected them in gravitational waves from colliding black holes. We've measured them in the redshift of distant galaxies. But understanding the mathematics, being able to calculate and predict these effects, isn't quite the same as understanding what they mean. When we say space-time is curved, what does that really mean? When we say time passes at different rates, what is time? These questions take us into deeper territory. They ask us to reconsider not just how the universe works, but what reality itself is, what time is, what it means for something to exist. We're going to continue exploring these questions. We're going to think about the nature of time and consciousness, about whether the flow of time is real or illusory. We're going to consider what it means for reality to depend on the observer. We're going to reflect on what Einstein left behind and what mysteries remain. But for now, let's take a moment to breathe and absorb what we've already covered. Space-time is curved, gravity is geometry, the universe is expanding, and reality is stranger and more beautiful than our everyday experience suggests. What space-time does to our minds. Let's think about motion in a new way. In space-time, the history of an object isn't just a series of positions at different times. It's a single, unified path through four-dimensional space-time, called a world line. Imagine you're sitting in a chair reading this. You're not moving through space, but you're moving through time. Your world line extends from the past to the future, straight up through the time dimension. Now imagine you stand up and walk across the room. Your world line tilts. It's now angled through both space and time, representing your motion through both dimensions. From the space-time perspective, your entire life is a single world line, stretching from your birth to your death, weaving through the four dimensions of space-time. Every event in your life is a point on that world line. This way of thinking about time, called the block universe, or eternalism, is natural when thinking about space-time. In this view, the past, present, and future all exist in the same way. They're all part of the space-time structure. The flow of time, the sense that the present moment is somehow special and real while the past is gone and the future doesn't exist yet, is a feature of our consciousness, our subjective experience, not a feature of space-time itself. This idea is deeply strange. It suggests that in some sense, all moments in time exist equally. Your birth and your death are both points in space-time, both equally real, just located at different temporal coordinates. If this is true, then what we call the passage of time, the feeling that we're moving from past to future, is an illusion. Or at least, it's a feature of how we experience space-time, not a fundamental property of space-time itself. Some physicists and philosophers embrace this view. They argue that space-time is like a landscape, a fixed four-dimensional structure, and our sense of moving through time is like a perspective effect, the way a traveler experiences different parts of a landscape as they move through it. Others resist this view. They argue that there's something special about the present moment, something that can't be captured by the mathematical description of space-time. They point to the fact that we can remember the past, but not the future, that we can influence the future, but not the past, as evidence that time has a real direction, a flow that isn't just subjective. This debate connects to deep questions about free will, consciousness, and the nature of existence. And it's a debate that still continues. What's clear is that Einstein's spacetime gives us a new way of thinking about time. It's no longer simply a universal flow. It's a dimension, woven together with space, experienced differently by different observers, but existing as part of a four-dimensional structure that, in some sense, simply is. There's another aspect of time that Einstein's theories don't fully address, one that might be even more puzzling than the physics. Our subjective experience of time, the feeling of now, the sense that time flows from past to future. Physics can describe how clocks behave, how time is measured, how it's affected by motion and gravity. But it doesn't really explain why we experience time the way we do. It doesn't tell us why we have this persistent feeling of moving through time, of the present moment being special and real in a way that other moments aren't. We remember the past, but not the future. We can influence the future, but not the past. We feel like we're moving through time from a definite past toward an open future. The present moment feels special, immediate, in a way that past and future moments don't. But in the space-time picture we've been discussing, all moments exist equally in the four-dimensional structure. Past, present, and future are all part of the geometry. There's no objective flow of time, no universal now moving through the universe. So where does our experience of time come from? Why do we feel time flowing if, from the space-time perspective, all moments just are, existing eternally in the four-dimensional structure? This is one of the deepest unsolved problems in physics and philosophy, and there are several different approaches to answering it. Some researchers believe it has to do with the second law of thermodynamics, the principle that entropy, or disorder, always increases with time in closed systems. A broken glass doesn't spontaneously reassemble. Heat flows from hot to cold, never the reverse. Eggs can be scrambled, but not unscrambled. This increase of entropy gives time a direction, an arrow pointing from past to future, and it might be connected to our psychological experience of time. Our memories are physical structures in our brains, records of past states encoded in neural connections. Creating a memory increases entropy. We can remember the past because those records exist. We can't remember the future because those records haven't been created yet. Similarly, we can influence the future because our actions create new patterns, new structures, increasing entropy as we go. But we can't influence the past because that would require decreasing entropy, reversing the natural flow from order to disorder. So perhaps our sense of time flowing, of moving from past to future, is intimately connected to the increase of entropy, to the thermodynamic arrow of time. But this doesn't fully explain the feeling of now, the sense that this moment, right now, is happening while other moments are either gone or not yet real. Why does it feel like only the present exists? Some philosophers and physicists argue that this is an illusion, that the feeling of now is a feature of consciousness, not a feature of physical reality. In this view, called the block universe, or eternalism, all moments in time exist equally. Your birth, your current experience reading this, your eventual death, all exist as points in space-time. The feeling that only the present is real is a cognitive phenomenon, a way your brain processes information, not a fundamental property of the universe. Others resist this view. They argue that there is something objectively special about the present moment, something that physics doesn't yet fully capture. They point to the fact that quantum mechanics seems to involve the collapse of possibilities into actualities, a process that happens in the present and creates the past. In this view, called presentism, only the present moment exists. The past is gone, finished, no longer real. The future is open, not yet determined, not yet real. Time genuinely flows, and physics needs to account for this flow. There's no consensus on which view is correct, and the debate connects to other deep questions about consciousness, free will, and the nature of reality. Some researchers are exploring how quantum mechanics might affect our understanding of time. Quantum mechanics introduces fundamental uncertainty and randomness into physics. Before you measure a quantum system, it exists in a superposition of possible states. The measurement collapses this superposition into a definite outcome. Could this quantum uncertainty be related to the openness of the future, to the feeling that the future isn't yet determined? Some physicists think so, though this remains speculative. Others are studying how the brain creates our sense of time. Neuroscientists have found that our perception of time is flexible, constructed by the brain from various inputs. Time can seem to pass quickly or slowly, depending on our mental state. Our sense of the present moment actually spans a fraction of a second, not an instantaneous point. Perhaps our feeling of time flowing is a feature of how our brains process information, create narratives, build models of the world. Perhaps the flow of time is real only from the perspective of conscious beings embedded in the universe, not from an objective external viewpoint. We simply don't know. The relationship between time as described by physics and time as we experience it remains one of the great unsolved mysteries. What we can say is that Einstein's space-time gives us a powerful framework for understanding the physical behavior of time. It tells us how clocks tick, how motion affects duration, how gravity warps the flow of time. But it doesn't fully explain the feeling of time passing, the sensation of being in the now, the subjective experience of moving from past to future. That mystery remains open, waiting for deeper insights that might come from physics, neuroscience, philosophy, or some combination of all three. The observer-dependent universe. Let's think once more about what it means for reality to depend on the observer, because this is one of the most philosophically challenging aspects of Einstein's relativity. In Einstein's universe, there's no God's eye view, no perspective from outside space-time that sees things as they really are, independent of any observer. Every observer has their own perspective, their own division of space-time into space and time, their own notion of simultaneity and duration. And all of these perspectives are equally valid. None is more correct than any other. None reveals the true nature of reality in a way the others don't. This is a radical departure from how we normally think about reality. We tend to assume there's an objective world out there, existing independently of observers, and our observations are just imperfect glimpses of that objective reality. We might have different perspectives, different angles, different viewpoints, but we're all looking at the same underlying reality. But relativity suggests that observation is more fundamental than that. Reality is always reality from a perspective. There is no perspective independent description of when and where things happen, at least not for events separated enough that they can't causally influence each other. This doesn't mean reality is purely subjective, that truth is relative, that everyone can believe whatever they want, and all beliefs are equally valid. That's not what relativity says at all. There are still objective facts. The structure of space-time itself is objective. The world lines of particles through space-time are objective. Whether two events can causally influence each other is objective. The laws of physics are objective. What's observer-dependent is the division of space-time into space and time, the determination of what's happening now versus what happened in the past or will happen in the future, the measurement of spatial distances and temporal durations. Different observers, moving differently through space-time, slice the four-dimensional structure in different ways. They divide it differently into 3 dimensions of space and 1 of time. And from these different slicings come different measurements, different descriptions of when and where things happen. But all these different descriptions are consistent with each other. They're different perspectives on the same underlying space-time geometry. You can translate from one perspective to another using the mathematics of relativity, the Lorentz transformations that connect different reference frames. Think of it like looking at a 3-dimensional object from different angles. Each angle gives you a different 2-dimensional view of the object. The views look different, emphasize different features, have different shapes and proportions, but they're all views of the same object. You can use geometry to figure out how one view relates to another. Similarly, different observers have different views of space-time, different divisions into space and time, but they're all views of the same 4-dimensional structure. The underlying geometry is objective, even though the perspectives are different. This is subtle but important. Relativity doesn't say that objective reality doesn't exist. It says that certain things we thought were objective, like simultaneity in the present moment, are actually perspective-dependent. But there's still an objective space-time structure that all perspectives are perspectives on. There's a famous thought experiment called the twin paradox that we touched on earlier, but it's worth revisiting in more depth because it illustrates these ideas beautifully. One twin stays on Earth, the other travels in a fast-moving spacecraft, then returns. When they reunite, the traveling twin is younger. Less time has passed for them. But here's the puzzle that makes it a paradox. From the perspective of the traveling twin, couldn't we say that Earth and the stay-at-home twin were the ones moving away and returning? Shouldn't the stay-at-home twin be the younger one? The resolution is that the situation is not symmetric. The traveling twin changes their state of motion. They accelerate to leave Earth, then decelerate and accelerate again to turn around and come back. This acceleration breaks the symmetry. The traveling twin's reference frame changes during the journey, while the Earthbound twin's remains constant. In space-time terms, the two twins follow different world lines through space-time, different paths. One world line is straight, representing constant motion through time with no motion through space. The other world line is curved, representing motion through both space and time, with changes in direction. And the amount of time experienced along a world line, what we call proper time, depends on the path through spacetime. Different paths can have different proper times, just as different routes between two cities can have different distances. The twin who accelerates follows a curved path through spacetime and experiences less proper time. The twin who doesn't accelerate follows a straight path and experiences more proper time. Both twins' measurements are correct from their own perspectives, but spacetime itself provides an objective structure that all observers can agree on. The world lines are objective. The proper time along each world line is objective, and these objective facts are agreed upon by all observers. This resolution shows how relativity works. Different observers have different perspectives, different divisions of space-time, but there's still an objective geometric structure that all observers can agree on, and that structure determines what actually happens. Reality depends on the observer in the sense that different observers slice space-time differently, but reality is objective in the sense that the space-time structure itself is observer-independent, and all the observer-dependent descriptions are consistent perspectives on that objective structure. The mysteries that remain. We've been on a long journey through space-time, from the simple idea that space and time are connected, to time dilation and length contraction, to curved space-time and gravity, to black holes and the expansion of the universe itself. Along the way, we've seen that reality is stranger than our everyday intuition suggests. Time is not universal, space is not fixed. Simultaneity depends on motion. Gravity is curvature. The universe is expanding. Black holes exist. Space-time can ripple with gravitational waves. All of these ideas come from Einstein's theories of relativity, special and general. And these theories have been tested extensively, confirmed by countless experiments and observations over more than a century. They work. They describe the universe with extraordinary precision. We can use general relativity to predict the orbits of satellites with accuracy measured in millimeters. We can calculate the exact amount by which light will bend around a distant galaxy. We can predict the waveform of gravitational waves from colliding black holes and compare our predictions to observations, finding them matching to incredible precision. The mathematics of general relativity is beautiful and elegant. Einstein's field equations, which describe how matter and energy curve space-time, can be written in a form that fits on a single line. Yet from those equations flows all the rich complexity we've been discussing: time dilation, curved space, black holes, gravitational waves, the expansion of the universe. But there are limits to what we understand. General relativity breaks down at singularities, at the centers of black holes, and at the beginning of the universe. At these places, space-time curvature becomes infinite, and our equations stop making sense. They give us infinities, mathematical expressions that don't correspond to anything physical. Most physicists believe this indicates that general relativity is incomplete, that it's an approximation that works brilliantly under most circumstances, but fails in the most extreme conditions. We need a deeper theory to understand what happens at singularities. That deeper theory would likely be a quantum theory of gravity, a theory that combines general relativity with quantum mechanics, the other great pillar of modern physics. Quantum mechanics describes the behavior of particles and fields at the smallest scales, the realm of atoms and subatomic particles. It's been tested as thoroughly as relativity and has passed every test. But quantum mechanics and general relativity use different mathematical frameworks, different ways of thinking about reality. They're difficult to reconcile. In quantum mechanics, space and time are treated as a fixed background. Particles move through space and evolve in time according to quantum rules. But space and time themselves don't change. They're absolute, much like in Newton's physics. But in general relativity, space-time is dynamic. It curves, it ripples, it expands. It's not a fixed background, but an active participant in physics. Combining these two perspectives has proven extraordinarily difficult. For almost a century, physicists have been trying to develop a theory of quantum gravity. There are candidates, like string theory and loop quantum gravity, but we don't yet have experimental evidence to tell us which, if any, is correct. Without quantum gravity, we can't fully understand black hole singularities. We can't describe the very first moments of the Big Bang, the earliest instance when the universe was so small and dense that quantum effects would have been important. We can't answer questions like what happened before the universe began, or whether that question even makes sense. And there are other mysteries. We don't know what dark matter is, the invisible substance that makes up about 27% of the universe's mass and energy. We observe its gravitational effects, see how it shapes the rotation of galaxies and the motion of galaxy clusters, but we haven't directly detected the particles that make it up. We don't know what dark energy is, the mysterious energy driving the accelerating expansion of the universe. Is it Einstein's cosmological constant? Is it some exotic field? Is it telling us that general relativity needs modification on cosmic scales? We don't fully understand why the universe is expanding and why that expansion is accelerating. We can describe it mathematically, fit it into our equations, but we don't know the underlying mechanism. And we don't understand the nature of time itself, how the physical time described by relativity relates to our subjective experience of time flowing from past to future. This is a question that touches physics, philosophy, and neuroscience, and we're far from a complete answer. Einstein's spacetime gives us a framework for thinking about these questions, a language for asking them precisely. But the framework doesn't answer all of them. The universe is still mysterious in deep and profound ways. That's not a failing of the theory. It's a recognition that there are limits to our current understanding, frontiers we haven't yet crossed, mysteries we're still working to solve. Science is an ongoing process, not a finished product. Each answer leads to new questions. Each discovery reveals new mysteries, and that's part of what makes it exciting. Einstein died in April 1955 at the age of 76 of an aortic aneurysm. He had spent his final years still working on physics, still searching for a deeper understanding of nature, still asking fundamental questions about the universe. In the 7 decades since his death, his theories have been tested and confirmed in ways he could never have imagined. We've sent atomic clocks on airplanes and satellites and measured time dilation with extraordinary precision. We've observed light bending around galaxies and black holes. We've photographed the shadows of black holes. We've detected gravitational waves from merging black holes a billion light-years away. General relativity has become one of the most precisely tested theories in all of science. Every prediction has been confirmed, often to many decimal places of accuracy. The theory works spectacularly well across an enormous range of scales and conditions. GPS satellites use relativity to keep their clocks synchronized. Astrophysicists use it to model black holes and the expansion of the universe. Gravitational wave detectors use it to predict the waveforms they're looking for. The theory is not just beautiful mathematics. It's practical, applicable, essential for understanding and navigating the universe. But Einstein's work also raised profound questions that we're still grappling with. mysteries that remain unsolved despite a century of effort. What is the relationship between space-time and quantum mechanics? How do we describe space-time at the smallest scales, where quantum effects become important? What happens at the singularities inside black holes and at the beginning of the universe? Our current theories break down at these places, giving us infinities that don't correspond to physical reality. What is dark matter? The invisible substance that makes up about 27% of the universe's mass and energy. We observe its gravitational effects, see how it shapes the motion of galaxies and the large-scale structure of the universe, but we haven't directly detected the particles that compose it. We don't know what it is. What is dark energy? The mysterious energy driving the accelerating expansion of the universe. Is it Einstein's cosmological constant, a fundamental property of empty space? Is it some exotic field or energy we don't yet understand? It makes up about 68% of the universe's energy, but its nature remains unknown. Why is the universe expanding? And why is that expansion accelerating? We can describe it mathematically, fit it into Einstein's equations, measure it observationally, but we don't fully understand the underlying mechanism, the reason why space-time behaves this way on cosmic scales. Is the block universe picture correct, with all moments in time existing equally in the four-dimensional structure? Or is there something special about the present moment that current physics doesn't capture? Does the future already exist in the same way the past does? Or is it genuinely open and undetermined? What is the nature of time itself? Why do we experience it flowing from past to future? Why can we remember the past but not the future? How does the physical time described by relativity relate to our subjective conscious experience of time? These questions go to the heart of what space-time is and what it means for our understanding of reality. They connect physics to philosophy, to questions about causality and determinism, consciousness and free will, existence and becoming. Einstein gave us the tools to ask these questions in a precise scientific way. His theories provide the framework within which we explore them. But the answers, many of them, remain unknown. The universe still holds its secrets. And that's part of what makes this topic so endlessly fascinating. More than a century after Einstein's breakthrough, space-time is still revealing new aspects, still surprising us, still challenging our understanding. The story isn't finished, it's ongoing. And future generations will build on Einstein's foundation, discovering new phenomena, developing new theories, uncovering new layers of the mystery. There's something both wonderful and humbling about space-time. We can describe it mathematically with extraordinary precision. We can make predictions that match observations to many decimal places. We can test those predictions in laboratories and observatories around the world. We can use our understanding to build technologies like GPS that work reliably every day. But at a deeper level, we don't fully understand what space-time is. We don't know if it's fundamental or emergent, continuous or discrete, an independent entity or a relational structure defined by events. Modern physics is exploring these questions. Some theories propose that space-time is not fundamental but emerges from something deeper, perhaps from quantum entanglement or information theory. In these approaches, space-time is like temperature or pressure, a useful concept that emerges from more fundamental microscopic processes but doesn't exist at the deepest level. Other approaches treat space-time as fundamental but try to describe it quantum mechanically. Loop quantum gravity, for instance, proposes that space is made of discrete chunks, tiny loops of space-time about 10 to the minus 35 meters across, the Planck length. At scales larger than this, space appears continuous, but at the smallest scales, it's granular. String theory takes a different approach, proposing that the fundamental entities are not particles, but tiny vibrating strings existing in a space-time with more than 4 dimensions. The extra dimensions are curled up so small that we can't perceive them directly, but they affect the properties of particles and forces. These theories are mathematically sophisticated and make contact with general relativity and quantum mechanics in various limits. But we don't yet have experimental evidence to confirm or refute them. They remain speculative, awaiting observations that might distinguish between them. And then there are the philosophical questions that physics alone might not be able to answer. Is space-time real, or just a mathematical model? Does time genuinely flow, or is that an illusion of consciousness? Is the future open or determined? What does it mean for something to exist? We don't know. And it's possible that some of these questions don't have purely scientific answers, that they touch on aspects of reality that go beyond what can be measured and tested. Einstein himself was deeply interested in these philosophical dimensions. He thought carefully about the nature of time, about what it means for simultaneity to be relative, about the implications of his theories for our understanding of reality. He famously said, "The distinction between past, present, and future is only a stubbornly persistent illusion." This was in a letter to the family of his lifelong friend, Michel Bessot, written shortly after Bessot's death. Einstein was contemplating the nature of time and mortality, finding some comfort in the idea that from the space-time perspective, all moments exist eternally. But even Einstein didn't claim to have all the answers. He recognized that his theories, as successful as they were, might be approximations, effective descriptions that work brilliantly within their domain, but break down under extreme conditions or at very small scales. He spent the last decades of his life searching for a unified theory that would combine gravity and electromagnetism, that would show how all the forces of nature fit together. He didn't succeed. The problem turned out to be even more complex than he imagined, requiring not just unifying gravity and electromagnetism, but also incorporating the strong and weak nuclear forces and quantum mechanics. That quest continues today in different forms. Physicists are still searching for a theory of everything, a unified framework that would explain all the fundamental forces and particles. That would reconcile general relativity and quantum mechanics. That would answer the deepest questions about the nature of reality. We don't have that theory yet. But the search itself drives progress, leads to new insights, reveals new connections. And through it all, Einstein's spacetime remains the foundation, the framework within which we understand gravity, cosmology, and the large-scale structure of the universe. It's been tested thoroughly and has passed every test. It works, but working isn't the same as being final or complete. Science is always provisional, always open to revision in light of new evidence. And there are hints in the incompatibility between general relativity and quantum mechanics, in the mysteries of dark matter and dark energy, that we're missing something, that there are deeper layers still to uncover. Wonder at the strange and beautiful, even after this long exploration, even after understanding time dilation and curved spacetime, and observer-dependent reality, even after grasping the mathematics and confirming the predictions, something strange remains. The universe we inhabit is not the universe we thought we inhabited when we started this journey. The steady flow of time, the fixed stage of space, the objective reality that exists the same for all observers, all of these comfortable, intuitive assumptions turn out to be approximations, useful in our everyday slow-moving lives, but incomplete at a deeper level. What replaces them is more subtle, more interconnected, more dependent on perspective. Space-time is a unified structure, a four-dimensional fabric that can bend and ripple and expand. Time is woven together with space, inseparable. Motion through one affects experience of the other. Mass and energy curve the very geometry of existence. Different observers, moving differently through space-time, experience reality differently, and both their experiences are equally real, equally valid. There's no single universal description of when and where things happen, at least not for events that can't causally influence each other. And somehow, all of this follows precise mathematical laws. The curvature of spacetime is not random or chaotic. It's determined by the distribution of mass and energy through Einstein's elegant field equations. The behavior of objects moving through spacetime follows predictable paths, geodesics through the curved geometry. There's a deep order underlying the strangeness, a mathematical coherence that allows us to make sense of it even when it contradicts our intuitions. The equations work. The predictions match observations. The theory hangs together beautifully. But that order, that mathematical precision, doesn't remove the fundamental strangeness. It just makes the strangeness comprehensible, expressible in equations, testable through experiment. The universe is strange. Time dilates. Space curves. Reality depends on the observer. These aren't metaphors or approximations. They're how the universe actually works, confirmed by countless experiments and observations over more than a century. And we're still coming to terms with what that means. We're near the end now. We've traveled from the familiar experience of sitting still, feeling time pass at a steady rate, to the strange and subtle reality of space-time, where time is flexible, space is curved, and reality depends on perspective. Along the way, we've encountered ideas that challenge our intuitions, that ask us to rethink what we mean by time, by space, by reality itself. We've seen how motion affects time, how mass curves space-time, how observers moving differently can experience different realities, all equally valid. And through it all, there's been a thread of wonder that the universe is so much richer than it appears on the surface. Wonder that beneath the familiar, comfortable world of everyday experience lies this intricate, interconnected structure. Wonder that we can understand it, at least partially, through mathematics and observation and careful thought. Einstein's spacetime is not just a scientific theory, a collection of equations and predictions. It's an invitation to see the world differently, to recognize that the obvious is not always true, that the familiar is not always fundamental. It reminds us that we inhabit a universe that is strange and beautiful, ordered yet mysterious, knowable yet ultimately beyond complete comprehension. It shows us that reality is deeper than it appears, that time and space are not what we thought they were, that the universe rewards careful observation and rigorous thinking with insights that transform our understanding. And it leaves us with questions, mysteries that remain even after a century of study. Questions about the nature of time, about quantum gravity, about dark matter and dark energy, about what space-time fundamentally is. These questions are not failures of the theory. They're invitations to keep exploring, to keep asking, to keep searching for deeper understanding. Returning to the ordinary, extraordinary return for a moment to that feeling of sitting still, the feeling we started with so long ago. You're not moving through space. The room around you is stationary. Time is passing at its normal, steady rate. But now you know that this simplicity is deceptive, that beneath the surface lies something far more complex and strange. You are moving through space-time, always, constantly, inevitably. Even sitting still, you're traveling through time at nearly the maximum rate possible, because you're not moving much through the spatial dimensions. Every second, you advance 1 second into the future, following your world line through the four-dimensional structure of space-time. The room around you is not truly stationary. Nothing is truly stationary in any absolute sense. Earth is rotating on its axis at about 1,000 miles per hour at the equator. Earth is orbiting the Sun at about 67,000 miles per hour. The solar system is orbiting the center of the Milky Way galaxy at about 500,000 miles per hour. The galaxy itself is moving through space at hundreds of miles per second relative to other galaxies. And space itself is expanding, carrying everything along, creating more distance between distant galaxies every moment. Time is passing for you, but not at exactly the same rate it's passing for everyone else. Someone moving faster than you experiences time more slowly. Someone in a stronger gravitational field experiences time more slowly. The differences are usually tiny, unmeasurable without atomic clocks, but they're real. There is no universal now, no cosmic present moment that you share with everyone in the universe. Your now, your present moment, is defined by your motion through spacetime. Someone moving differently slices spacetime differently, has a different now. That includes events in your past or your future. The floor beneath you, the chair you're sitting in, these solid objects are mostly empty space, with atoms held together by electromagnetic forces. Particles following quantum rules we barely understand. And all of it exists within curved space-time shaped by Earth's mass, following the geometry described by Einstein's equations. The gravity you feel, the weight pressing you into your chair, isn't a force pulling you down. It's the curvature of space-time. The chair is pushing you away from your natural geodesic through curved space-time. And that push is what you feel as weight. What feels simple, what feels steady and solid and constant, is actually a complex interplay of motion, curvature, quantum mechanics, and perspective within a four-dimensional structure that we're only beginning to understand fully. This is what Einstein revealed to us. The familiar world is strange when you look closely enough. The everyday is extraordinary when you understand what's really happening beneath the surface. We've explored Einstein's idea of space-time from many angles, across many thousands of words, through thought experiments and real experiments, through mathematics and philosophy, through black holes and the expansion of the universe. We've looked at time dilation, length contraction, curved space-time, gravity as geometry, black holes as regions of extreme curvature, gravitational waves as ripples in the fabric of reality, the expansion of space itself carrying galaxies apart. We've discussed how reality depends on the observer, how the flow of time might be an illusion or a feature of consciousness, how our intuitions about time and space can profoundly mislead us. And yet, even after all of this, there's a sense in which we still don't fully understand what space-time is. We understand the mathematics. We can solve Einstein's equations for various situations. We can predict how clocks will behave, how light will bend, how the universe will evolve. The predictions match observations with extraordinary precision. But understanding the equations is not the same as understanding the reality they describe. What is space-time, really? Is it a substance, a physical thing that exists independently? Or is it just a mathematical framework for describing relationships between events? Is it fundamental? Or does it emerge from something deeper? Why does it have the properties it does? Why four dimensions, three of space and one of time? Why does time behave so differently from space, with a directionality that space doesn't have? Why is there space-time at all, rather than nothing? These questions take us to the edge of physics, to places where science meets philosophy, where our tools for understanding begin to run out, where different people give different answers, and there's no clear way to resolve the disagreements through experiment. Einstein gave us a profound insight into the nature of reality. He showed us that space and time are not what we thought they were, that they're woven together, that they're flexible and curved and observer-dependent. He gave us a mathematical framework that works beautifully, that makes predictions confirmed by countless experiments. But he also left us with a deeper mystery, the mystery of why the universe is this way, the mystery of what space-time fundamentally is at its deepest level. More than a century later, we're still exploring that mystery, still asking questions, still being surprised by what we find, still discovering new phenomena, from gravitational waves to black hole shadows to the accelerating expansion of the universe. And perhaps that's fitting. Perhaps the universe is under no obligation to make complete sense to us. to match our intuitions, to be simple or straightforward or fully comprehensible. All we can do is observe carefully, measure precisely, think clearly, calculate rigorously, and wonder at what we find. And what we find again and again is that reality is stranger and more beautiful than we imagined, that the universe rewards curiosity with insights that transform our understanding, that there are always deeper layers, always new questions, always more to discover. You're sitting somewhere quiet, and time is passing. This is where we started, with this simple observation, this familiar experience. But now you know that this simple statement contains depths you might never have imagined. Time is passing, but not at the same rate for everyone. Time is passing, but only because you're moving through space-time, following a world line through the four-dimensional structure. Time is passing, but that passage might be more about your experience, your consciousness, your subjective sense of moving from moment to moment, than about the fundamental nature of reality. Space surrounds you, but it's not the fixed, unchanging stage you thought it was. It's curved by mass and energy, following Einstein's field equations. It's expanding on the largest scales, carrying distant galaxies away from us. It's woven together with time into a single, unified structure that can ripple and wave. You exist at a particular place in time, but from another perspective, from someone moving differently through space-time, that place and time are different. Reality itself depends on the observer, on how they're slicing space-time into space and time. All of this is strange, deeply, fundamentally, profoundly strange. It contradicts our intuitions, challenges our assumptions, asks us to rethink what we mean by existence itself. But it's also real. It's how the universe actually works, as far as we can tell from a century of careful observation and rigorous testing. It's not speculation or philosophy or science fiction. It's physics, confirmed by experiment, built into the technologies we use every day. Understanding it, even partially, changes how we see ourselves and our place in the cosmos. It reveals that we're part of something far larger and stranger than everyday experience suggests. It shows us that the universe is not what it seems on the surface. Einstein's idea of space-time is more than a century old now. We've tested it thoroughly, confirmed it in countless ways, built it into our understanding of the universe and our practical technologies. And yet, we're still discovering what it means, still exploring its implications, still being surprised by its depths and subtleties. Perhaps we'll never fully understand it. Perhaps space-time will always retain some element of mystery, some aspect that eludes complete comprehension, some question that remains just beyond our ability to answer. But the attempt to understand, the effort to see deeper, to question assumptions, to follow the evidence wherever it leads, that attempt is itself worthwhile. It's how we learn, how we grow, how we transform our understanding of reality. Einstein showed us that the universe is stranger and more beautiful than we imagined. He gave us new eyes to see reality, a new framework for understanding space and time, and gravity, and the large-scale structure of the cosmos. And what we see, when we look closely, is wonder. The kind of quiet, profound wonder that comes from recognizing that what seems simple is not simple at all. That beneath the familiar surface lies something deeper, something that challenges us, surprises us, invites us to keep looking, keep questioning, keep discovering. Space-time is Einstein's gift to us, not just the theory, but the invitation to see the world differently, to recognize that time is not what it seems, that space is not what it seems, that reality itself is richer, stranger, and more wonderful than our everyday experience suggests. And to sit with that knowledge, that strangeness, that wonder, and let it change how we see everything. To understand that the steady room around you, the passing seconds, the solid ground beneath you, All of it is part of something vast and strange and beautiful. Something we call space-time. Something we're still learning to understand. Something that Einstein showed us more than a century ago, and that still, to this day, we don't fully comprehend. But we keep trying, keep exploring, keep wondering, because that's what it means to be human, to ask questions about the universe, to seek understanding, to find beauty in the strange and the mysterious. And in that ongoing quest, in that never-ending exploration, we honor Einstein's legacy and continue the journey he began.